In this video, we're going to be doing an example of how to sketch a polynomial function. I do have some steps here for us that we are going to go through as we work through this example. The first thing we're going to do is find the intercepts. So let's first plug in x equals 0. F of 0 would then give me -2 times 3 squared times -5. -2 times 9 times -5 gives me 90. Wow. Then I'm going to find the x-intercepts. Which is when y equals 0. So I'm going to set my function equal to 0. Now, I chose this one because there is a lot of students that will then say there is a 0 at 0. But -2 is never equal to 0. There's no x there, so don't plug that in as a 0. I do have a repeated linear piece here. So x being -3 is going to be one of my zeros, and it has a multiplicity of 2. And then I have another binomial term. It's a linear term, and that's going to have a multiplicity of 1. So let's go ahead and just start sketching what this graph is going to look like. It's not probably going to be to scale very well because I have this y-intercept up here at 90, and then I have 2 x-intercepts, -3 and 5. Now, the next thing we would want to do is check for symmetry. Since my zeros are not at the same x value plus or minus, I'm not going to have an even function. And I don't really think I'm going to have perfect symmetry between the first and second quadrant because I don't go through the origin. So I don't really think I'm going to have any symmetry here. All right, use the multiplicities of the zeros to determine the behavior of the polynomial at that x-intercept. Well, at -3, since I have a multiplicity of 2, my 0 is going to have a bounce. At x equals 5, since I have a multiplicity of 1, I'm going to just go through like so. Determine the end behavior by examining the leading term. So I could expand this if I wanted to, but I really could just look at my leading pieces and realize my leading term with this expansion would be -2 times x squared times x, or -2 x to the third. Since it's x to the third, I know that I will either have behavior that goes down and then up, or the other way. And then the negative term in the front for my leading coefficient tells me that this must be true. Ensure that the number of turning points does not exceed 1 less than the degree of the polynomial. Perfect. So our degree is 3. The number of turning points must be 2 or smaller. So let's see, if I connect this down to the 0 and I know that it's a bounce, it's going to look like this, and then I'm going to go up, and then I have to go through here. I only have 2 turning points, right? 1 and 2, wherever that is perfect. And then you can always check your answer on Desmos and make sure that you have done that correctly.